picture here is supposed to depict the Earth. I didn't do a particularly good job of drawing a good circle, but there it is. We're going to move from a point on the surface, and I'll note that at a point on the surface we're at 6,400 kilometers from the center of the Earth. We're going to let R stand for the distance from the center of the Earth. And we move 400 kilometers further away, so we're going to move to R equals 6,800 kilometers. There'd be a point out here. Now I've exaggerated that distance. That distance there would be more like close to 2,000 kilometers if everything was to scale. But we get the idea. So we're going to move from here to here. So here's our change in position. Now that could be our delta S, but we can't just do F dot delta S because the force is going to change as we move further away from the Earth. The Earth has less pull on it, just like if you move two magnets further apart, the pull drops off. Now the pull in the magnets drops off. You have a different force versus position profile for the magnet. But so if you could feel the gravitational force between two objects and pull them apart, it wouldn't feel quite like magnets. But as is the case with magnets, the force would fall off as you pull them apart. Okay, so as you increase the separation. Now, the acceleration of gravity now depends then on R, because the gravitational attraction, or the gravitational field, if you wish, decreases in magnitude as you move further away. So the gravitation, G is going to be a function of R, and that function is big G times big M over little r squared, where big G is the universal constant, equal to 6.67 times 10 to the negative 11th kilogram meter squared, Newton meter squared per kilogram squared, sorry. When multiplied by the mass of the Earth, which is what big M is, and then divided by the square of the distance, you get an acceleration in meters per second squared. Okay, and you don't need to worry too much about this expression now. I'm just using it to illustrate a point about potential energy. Okay, so this is a situation. We want to know how much work it takes to move a mass, little m, from here to here. Now, the problem with just trying to multiply your force by your delta S is that your force is variable. It changes with R. So you're going to have to do an integral. And there are a couple of ways to understand this. If we consider a graph of force versus position, the force exerted by gravity decreases as R increases, so that we have a curve that has this characteristic. It's an inverse square curve, and it has the characteristics of the inverse square function. Now, if we move from distance R1 to distance R2, we can pretend that the force changes linearly from here to here. But it doesn't, of course. It's down below this linear approximation. But here's the force at distance R1. Here's the force at distance R2. We could average these two forces and multiply by the distance R1 to R2. The average that we would get from this straight line approximation, if this is the way the curve looks, isn't too much different from the actual average force as calculated from the area under the curve. In other words, the area under this chord here is very close to the area under the curve because we're on a small part of the curve. Now, if the curve is like this and we cut across it from here to here, there's quite a bit of difference between the area under the straight line and the area under the curve. So our straight line approximation, where we just average the initial and final forces, is not a very good approximation of the area under the actual curve. Now, why are we interested in the area under the curve? Well, if we multiply an average force by a change in position, we get work. So the area under this curve is work. The area of any tiny trapezoid on this curve, under this curve, is going to be a very good approximation to the work done on that small subinterval, because the chords corresponding to the tops of these trapezoids stay very close to the curve in the limit. As the width of the trapezoids approaches 0, and of course the number of trapezoids approaches infinity, we get perfect match, meaning that the total work done is equal to the area under the curve. Now, I could go into more detail on that whole argument, but hark back to the information I gave you early in the term and ask you to be sure you understand. So it should be very clear why the integral then of the force with respect to the position in this situation is going to give us the total work. Okay. Now, you'll see situations where you want to average the initial and final force, and sometimes that gives you a very good approximation. But if you can do the integral, you get the accurate result. So the force is big G, big M, little m over r squared, as we indicate here, and that's just obtained by multiplying the mass m by the acceleration of gravity. And we can think of this as the force we exert. Now, I'm actually going to change this a little bit to, well, let me debate about that. I'm not sure I want to change. I'm thinking of changing the force to the force exerted by gravity. Okay, I did decide to change the signs. Now, this is just the magnitude of the force, but we know that the force exerted on the mass m by gravity is this way, and we're moving this way, so we know that the work done is going to be negative. So the work done by gravity is the negative of the integral from the 6,400 to the 6,800 kilometer position of the G big M little m over r squared with respect to r. Now, when we do that integral, it's very straightforward. We just factor out the constants big G big M little m, and we're left with the integral of negative 1 over r squared, and the integral of 1 over r squared being negative 1 over r, the derivative of negative 1 over r squared, or antiderivative, is going to be plus 1 over r, and that's going to be evaluated between 6,400 and 6,800 kilometers. So that what we have is, well, we have big G big M little m times 1 over r, so that's big G big M little m over r at 6,800 kilometers minus the value of that same expression at 6,400 kilometers. That's what? That's the change in the expression big G big M little m over r. A definite integral is just a change in the value of the antiderivative between the two limits. So that what we have here is the change in big G big M little m over r. And of course, if we know big G and big M and little m, we can plug in all the numbers. They're going to be compatible. We'll probably need to, well, I'm not going to go into the details of that. If we're given the information, we can calculate this, the two distances and the three masses, the two masses and the gravitational constant. Okay, now the point though is that the work done by gravity is then this change, which is equal and opposite to the change in potential energy from here to here. Now, what would you expect the change in potential energy to be from here to here? Or what sign would you expect it to have? Would the change be positive or negative? Well, we know when we move something away from the center of the Earth, when we lift something, we're moving it away from the center of the Earth. And by now we should have the intuition that that corresponds to an increase in potential energy. So it's pretty obvious that this should be an increase in potential energy. But this change is said to be equal and opposite, equal to the negative of the change in potential energy. So that the change in potential energy is the negative of this thing. Now, where does that leave us? Well, the change in potential energy should be positive, but it looks like it's negative. but it's really not negative because, why? Because R is getting bigger. We're going from 6,400 to 6,800 kilometers, and as R gets bigger, what happens to this expression? Well, it gets smaller. So the change in the G big M, little m over R is negative. So the change in potential energy is indeed positive. Now, I mention all this simply because it, I think, does a good job of illustrating the fact that the signs involved in applying energy conservation will drive you nuts if you're not very careful with them. Okay. Anyhow, so we have this expression for change in potential energy due to the Earth's gravity. Now, my big point is that doesn't look anything like mgy. Okay, so that's not to mgy or mgh, which is the formula that's often given in a textbook for gravitational potential energy. And that actually works okay as long as you're not in a situation where the gravitational force is decreasing. The gravitational field can't be changing significantly. And in this case, let's just note that R changes by 400 kilometers, which is about 6% of the 6,600 kilometer average distance, but it's pretty close to 6% of either the first or the second distance. And that causes this expression to decrease because bigger R gives you smaller G. Not only that, but since you're squaring R, it causes it to decrease by a percent that's approximately double the 6%. Now, they would be making use of the fact that a small percent change, when you square it, gives you twice as much percent change. And that's a simple principle, and it's fairly easy to see that just based on high school algebra. So whether you completely understand that or not, the point we're making is that you do have a 12% change in the force exerted by gravity on this mass. So you can't just use mgy. Y would be 400 kilometers. G would be whatever it is at the surface of the Earth, 9.8 meters per second squared. It wouldn't be decreasing by that 6%. And you wouldn't get an accurate result. And if you're actually trying to shoot a spacecraft up to that height, you're going to badly miscalculate the amount of fuel you need.